Now in this video, the proof of the result, any set of n plus 1 vectors in an n-dimensional vector space is linearly dependent is presented. Now consider this lemma. It is in this lemma that result is established. If v1, v2 and so on vn is a basis of v over f, and if w1 etc. wm in v are linearly independent over f, then m is less than or equal to n. That is, it says that if dimension of v is n, and if we have m number of linearly independent vectors, the relation between this m and this n is m is less than or equal to n. Now we will assume v to be of a vector space and s to be this collection. Then as s is given as a basis, s should span v. So L of s equals v. And S prime we shall consider to be this collection w1, w2 and so on wm. We need to have, whenever this S prime is linearly independent, m should be less than or equal to n. So we will assume the contrary, that suppose S prime is linearly independent in V for m greater than n. So we shall name this as statement P. Now S spans V, and therefore every vector in V, and in particular W1, which is also a member of V, is a linear combination of V1, V2 and so on Vn. So W1 can be written as alpha 1 V1 plus and so on alpha n Vn. Now taking this W1 to the other side, we have minus W1, which is written as the sum of all this plus minus 1 into W1 equal to 0. So this obviously tells us that there exists a scalar which is non-zero such that the linear combination is 0, which means these vectors should be linearly dependent. So we shall call that collection to be, already we have V1, V2, etc. Vn in the set S. Now with that we augment this set singleton W1, that is we have S1 to be the set consisting of W1, V1, V2 and so on Vn, which we simply denote as S union singleton W1. So this is linearly dependent in V. Now hence by theorem 4.2.14, which states that if V1 etc. Vn are in V, then either they are linearly independent or some Vk is a linear combination of the preceding ones, namely V1 etc. Vk minus 1. We have vector Vk which is not equal to W1 in S1, which is a linear combination of the preceding ones. So we have Vk being written in this way, delta W1 plus beta 1 V1 plus beta 2 V2 and so on plus beta k minus 1 Vk minus 1. We shall name this as equation 2. Now we shall take S2 to be S1, from which Vk is deleted. Okay, we delete Vk from S1. So S1 already we have S union that singleton W1. So from that we are deleting one Vk. So what we have is W1, this collection S2 to be the set consisting of W1, V1, V2, Vk will not be there, and the rest of the vectors of S will be present. Now we claim that this S2 spans V. Now L of S2 is always contained in V, so that part is left. And if V belongs to capital V, then by 1 we have V being written as, this is from Vk that we are writing, V is written as alpha 1 V1 plus alpha 2 V2 and so on alpha k Vk and so on up to alpha n Vn, and this Vk is replaced by this, that's given in equation 2. So this is what we have for V, and we collect the terms containing V1, V2 and so on Vk minus 1 up to alpha n Vn we have written, and this is obviously a linear combination of elements of S2. So you have all the elements excepting Vk, so you have that to be a linear combination of elements of S2, this one. So this V belongs to L of S2, and therefore V in capital V implies V belonging to L of S2. So capital V is contained in LFS2. Already LFS2 is contained in V, and here V contained in LFS2. So you have LFS2 to be the whole of V. That is, S2 spans V. Now, since S2 is contained in S and S is linearly independent, by result 4.2.12, which states that any non-empty subset of a set of linearly independent vectors is linearly independent, we have S2 to be linearly independent, and already S2 spans V. So S2 becomes a basis of V. Now, since L of S2 is V, every vector in V, and in particular W2, is a linear combination of elements of S2. So W2, which is a member of capital V, and V is spanned by this. So we can write W2 as the linear combination of these vectors. So this becomes lambda 1 V1 plus and so on, lambda k minus 1 Vk minus 1, then plus lambda k plus 1, etc. Alpha n Vn plus delta W1. See here some more terms are missing. So we have delta W1 plus minus 1 into W2 equal to 0. It's from this step it comes. These elements should be there. This expression, the entire expression is missing here, so that should be there. So when we bring this to the, or when we take this to the right side, this is what we get. So obviously we have, when we consider S3 to be this collection, that S3 is nothing but S2 union singleton W2, and that becomes linearly dependent because there exists a scalar which is non-zero, but yet the linear combination is 0. So we get S3 to be linearly dependent in V. Now by theorem again 4.2.14, as this is linearly dependent, we can have Vk to be a linear combination of the preceding vectors. So we have there exists a vector in S3 which is a linear combination of the preceding vectors. Since the Wi's are linearly independent, this vector cannot be W2 and W1, and hence must be some Vj where j is not equal to k, with j greater than k. So deletion of a Vj from, because that k is already, Vk is already accounted, that's why we are having this. Deletion of a Vj from the set S3 gives the set S4. So we have this S4 to be this collection, W2, W1, V1, V2 and so on. Vk is not there, Vj is also not there. So instead of them only these two have come. And from this we are we have how this one has come from S3, it has come, and from that Vj is deleted. So that's why we have this. And as we proved earlier, we can show that this L of S4 is also V. L of S2 equals V. We proved in the same way we can prove that L of S4 is V. So and this is what we had at each step. Whenever we include a W from S prime to S, we excluded a V from S, and the resulting set still spans V. So if M is greater than N, after repeating this process N times, we arrive at the set Wn, Wn minus 1 and so on W1, which spans V. But Wn plus 1 is a member of capital V. So Wn plus 1 is a linear combination of W1 etc. Wn. So that would imply that this collection is linearly dependent, which is a contradiction to statement P. So this was statement P. Suppose S prime is linearly independent in V for M greater than N. So but here we are getting N plus 1 vectors are there and it is linearly dependent. So more than n vector this one has. According to this, it should be linearly independent. That's our assumption. We assumed it wrongly, and that's why we are getting a contradiction here. So our conclusion should be M cannot be greater than N. It should be less than or equal to N. So the number of linearly independent vectors in an n-dimensional vector space should be less than or equal to N. Now this can be explained in the illustration with S consisting of just 2 elements and S prime consisting of 3 elements. Suppose we assume that S prime has linearly independent vectors cannot exceed the number of elements in a basis. So we are assuming S to be basis in this illustration, and we can consider 3 elements which are linearly independent. We have to get a contradiction. This cannot happen. That is what we are trying to establish. So we consider our S prime, that is this. From that S prime on W1 is augmented to S. So we have, but already S is basis, so it has to span V, that is there. And we have from S, we are augmenting, in to S we are augmenting this W1, so we get S1. And because this S1 is linearly dependent, some Vk, so here only 2 vectors that we have, so V2 will be linearly dependent on the previous vector, namely V1. So we exclude that V2 from this. So we arrive at S2. So we have deleted one V2 from S1. So we get S2. And to this S2 from S prime, W2 is supplied. And when we can get that, this is what we have. That is S3 is by augmenting S2. By augmenting W2, the singleton W2 with S2, we get S3. But this S2, already we know that it spans V. Already it's proved in the result that LFS2 equals V. So that is the part of our S2. And this S2 to S2, W2 augmented, so you get S3. Now this will be linearly dependent. So some Vk is a linear combination of its preceding vectors. V2 is already removed, so there is only one, that is V1. So that is removed from this. So we have the resultant set to be S4. And what does this S4 do? S4 still spans our V. So since W3, it's a member of S prime, and hence is a member of V, but S4 spans V, so we can write W3 to be a linear combination of W1 and W2. So we have W1, W2, W3 to be linearly dependent. That's a contradiction to this. We have said that this is linearly independent, and here we are getting linearly dependent. So that contradiction arose because we assumed the number of elements in the basis to be less than the number of elements in this collection. So this is what we have done. Given S prime, this one which is linearly independent, to that, from that we are taking W1 and supplying that. So we include this W1 to S, and that results in the exclusion of a V, and the resulting set still spans V. We include from S prime on W1 to S, and the resultant from the set S1, one V is because it's linearly dependent, one V2, one V is excluded. This inclusion results in the exclusion, and the resulting set still spans V. And again we include one W from S prime to this, and that results in this set. And once you have inclusion, one because of this in the nature of this S3 which is linearly dependent, we exclude one V1 from that. So we arrive at this, and the resultant set still spans V. So inclusion results in the exclusion, and the resultant still spans V. So when we proceed like this, ultimately we arrive at this collection which is linearly dependent, and that's a contradiction to our assumption. So this for the entire n-dimensional vector space is given in this slide. We have inclusion, exclusion, resultant spanning V. Inclusion, exclusion, and the resultant set spans V. So there are 4 corollaries to this lemma, and that will be established in the next video.